Before we train our model, let's define a couple of terms so we have a shared vocabulary to use while exploring model training. Gradient descent is an optimization algorithm that finds the minimum of a cost or loss function. It achieves this by iteratively adjusting the model parameters, the weights and biases that determine the equation of the prediction line, until it reaches the minimum loss or cost. A cost function, or loss function, is a mathematical function that quantifies the error between the model's predictions and the actual values. In our case, we'll be using a root mean squared cost function. Hyperparameters are configuration variables that influence the learning process. For example, learning rate, batch size, and epoch. Learning rate controls the size of the adjustments made while iterating through the training process. Batch size determines how many data points are taken into consideration in each iteration. And epoch controls how many complete passes through the training data are performed. Before we look at any source code, let's walk through a visual representation of what is happening behind the scenes while training our model. On the right-hand side, we've depicted a model plot. Fare, the value we are trying to predict, is on the y-axis, and trip miles, the value we are using to make our predictions, is on the x-axis. The blue points on the graph represent a few data points from our training data, and the red line is a candidate prediction line. The vertical black lines represent the distance between the predicted values and the actual values, or the model's error. On the left-hand side, we will plot our loss curve. The y-axis represents the model's error. In our case, since we're using a root mean squared loss function, it is the square root of the average squared distance between the predicted and actual fare values. The x-axis represents the training epoch hyperparameter for a specific training iteration. In our first training iteration, the model reads in batch size data points from our training data, calculates a candidate prediction line, measures the distance between the predicted and actual values, and determines the root mean squared error value. The model then uses the learning rate hyperparameter to make adjustments to the candidate prediction line with the goal of reducing the model error. The model then reads in the next batch size data points from the training data and performs the whole optimization process again. It continues to iterate through the training data in batch size chunks until it has processed all the training data, or completed the entire epoch. To simplify our visual representation, we are only updating our plots at the end of each epoch. As the model continues to iterate through the training process, we can see that the adjusted candidate prediction line is visually becoming more accurate. We can also quantify the improvement by looking at the loss curve and seeing that each successive training iteration has a lower root mean square error. Now that we have a better understanding of how model training works, let's look at our source and train our model.